We have a lot to cover today, and I want to make sure to get through all of it. We are going to go back and finish up these topics from chapter 7. Hopefully you guys all read the couple of pages about degrees of unsaturation like I asked you to over the weekend. Okay, somebody's put in the chat box about exam 2 grades. Exam 2 is graded, but I have not had a chance to kind of flip through and look through and get a sense of how people did yet. My plan is to be posting those grades later today. If not today, then tomorrow. And we'll talk more about that on Wednesday. Okay, so today, hopefully you guys all did read the couple of pages on degrees of unsaturation. We'll go over that in detail together today, and then we'll touch on these last couple of topics. So in order to get started with degrees of unsaturation, what I'd like to do first is remind you guys about something we've talked about previously. And this slide should look familiar from a slide last week and getting started on chapter 7. We talked about cis oleic acid and trans oleic acid and how the cis alkenes are naturally occurring fatty acids and they're considered good fats. We talked about how these are in olive oil and things like that. And that the trans fats are made synthetically by chemists in order to improve the shelf life of things like margarine. These are the types of double bonds in partially hydrogenated soybean oil or vegetable oil. They are not good for you and have serious implications linking them to heart disease. Both of these compounds, I said it when I introduced them last week, but you probably didn't notice it because you didn't understand the word, but both of these compounds are considered monounsaturated fatty acids. And in sort of pop culture, nutritional pop culture, you may have heard about monounsaturated fatty acids or polyunsaturated fatty acids or saturated fats. So in order to think about what unsaturated fats are, I'm going to show you an example of a saturated fat, and that's right here. This is stearic acid. This is a C18 chain with a carboxylic acid at one end. And this is one example of a saturated fat. Saturated fats, just so you guys know, are also naturally occurring, just like cis unsaturated fats are, but they're more prevalent in animal fats. And saturated fats, as you guys might know or have heard from kind of pop culture, they are not good for you either. These are not the healthy kind of fats. These fats are also associated with a lot of different disease states. Hopefully you guys can kind of see intuitively what we're talking about here in terms of saturated molecules like this saturated fat down in the bottom versus unsaturated like the 2 oleic acid examples up at the top. But I'm going to go ahead and define it for you. Whether we're talking about fatty acids like are on this slide or any molecule anywhere, doesn't have to be a fatty acid. A saturated molecule has the maximum number of hydrogen atoms that it could have for an acyclic version of that molecule. So we'll see examples that'll help this concept get driven home and make more sense to you guys. But this is the definition of saturated, is it has the maximum number of hydrogen atoms that is possible for an acyclic version of the molecule. And so you can see for this stearic acid, if we wanted to add more hydrogen atoms, we don't really have any place along this carbon chain to add any more hydrogen atoms. Whereas in the oleic acids, we could add 2 more hydrogen atoms to the double bonded carbons, right? 1 on each carbon. And so because we can add more hydrogen atoms to the double bonded carbons in these alkenes, they are considered unsaturated fats. Okay. This is just the same definition that I just said. A saturated molecule has the maximum number of hydrogen atoms possible for the acyclic version of that scaffold. And so when we talk about unsaturation, what we're talking about is an element in the molecule, a structural element in the molecule that requires taking away 2 hydrogen atoms, from the molecule. So if you want to make a double bond, you have to remove 2 hydrogen atoms to be able to open up the valency on each of those carbons to make that pi bond, to be able to open up the orbital to create the pi bond. you have to remove a hydrogen atom from each carbon. So it turns out that a ring, anytime you have a ring in a molecule, that is an element of unsaturation. Also, anytime you have a pi bond, that's another kind of element of unsaturation. And it turns out to be kind of useful, depending on the circumstance, to know how many degrees of unsaturation are in a molecule. So this term degrees of unsaturation is the same thing as asking how many elements of unsaturation there are. And there are two different ways that we can do this. The easiest way is to look at the structure. And then every time you have a ring and every time you have a pi bond, you count those things as 1 degree each. And so you can just add up the total number of rings and pi bonds in the structure, and that is how many degrees of unsaturation you have in a molecule. However, that relies on you knowing the structure of the molecule. And so if you went out on a hike and found some really cool looking plant and took it from its natural habitat, took it back to the lab and ground it up and isolated some cool compound from it, but you don't know what that compound is, you can't just look at the structure because you don't know what it is. So what you can do is do some experiments on that compound to get the molecular formula. And if you know the molecular formula, we can do a calculation to figure out how many degrees of unsaturation there are in that formula, because again, each degree of unsaturation involves decreasing the number of hydrogens in the molecule by 2. And we know that simple alkanes have this generic formula of CnH2n plus 2. So with those two pieces of information, we can calculate the degrees of unsaturation. So I'm going to show you each of these in depth over the next couple of slides, one slide for this one and several slides for this one. So here we go. First thing is looking at the structure and being able to see what's going on. And that's, again, counting the rings and the pi bonds. And this is going to be a lot easier than the alternative of calculating the degrees of unsaturation from the molecular formula, but we will go over that over the next couple of slides also. So if we just want to look at the structure and determine the number of degrees of unsaturation, I put up this series of C3 molecules in order to show you some examples here. So if we have propane, C3H8, propane has only single bonds and it's no rings. So it's a fully saturated molecule. And that should make sense also because the molecular formula fits with a CnH2n plus 2. But we're going to focus just on the structures here. If we go one to the right and we look at propene, we can see this propene has a double bond in it. So that double bond has a pi bond, which represents 1 degree or 1 element of unsaturation. If we were to take our propane and turn it into cyclopropane, we would have a ring, and that ring represents 1 degree of unsaturation. Now, in this last example on the far right, we have propyne, which is the 3-carbon molecule with a triple bond in it. Now, think back and remember that triple bond is made up of a sigma bond and 2 pi bonds, right? It has a pi bond going probably horizontally with respect to the screen, perpendicular to the screen, and a pi bond in the same plane as the screen. And so it has 2 distinct pi bonds in a triple bond. And so that means that this triple bond has 2 elements or 2 degrees of unsaturation. So the next couple of bullets just kind of reiterate that. Every ring counts as 1 degree of unsaturation. So here's cyclopropane with 1 degree of unsaturation. Every pi bond counts as 1 degree of unsaturation. But you have to remember a double bond is made up of a sigma and 1 pi. Triple bond is made up of a sigma and 2 pi. So if you have a double bond, that is 1 degree of unsaturation. If you have a triple bond, that is 2 degrees of unsaturation. Okay, and I mentioned this before, but in addition to degrees of unsaturation or elements of unsaturation, there are other names for this same thing. And I've listed out a couple of the other ones here. Double bond equivalence, or DBE, is another one that comes up a lot. I am almost always going to use degrees of unsaturation because that's just how I learned it and my personal preference. But if you take or go 2 with somebody else, they could theoretically use any of these terms. And those would be the same thing as my degrees of unsaturation. Okay, so now we know how to look at a molecule and figure out the degrees of unsaturation, but what if we don't have the structure? And I see there's a question in the chat box. All right, so the question in the chat box is, what if you have a benzene ring? Well, thank you for that. Let's do it. If you have a benzene ring, here's what benzene looks like. How many degrees of unsaturation do you guys think that is? 4. That's right. So there is one ring and there is 1, 2, 3 pi bonds. So that makes a total of 4. Benzene has 4 degrees of unsaturation. Thanks for the question. Okay, so what if we don't have a structure? Let's figure out how to calculate those degrees of unsaturation. We've already kind of danced around this a little bit, but let's go ahead and nail it down. First, in order to calculate the degrees of unsaturation, the first thing we need to do is figure out how many hydrogens would that molecule have if it were saturated, right? And in order to do that, we just apply our generic formula for simple alkanes of CnH2n plus 2. So we take however many carbons our molecule has, and we figure out how many hydrogens it would have if it were saturated. And then after we do that, we know that every 2 hydrogens that are missing equals 1 degree of unsaturation. So we just figure out the difference between how many we have and how many we should have and divide that difference by 2. So let's do an example. Oh, before we do the example, I do want to note, when we are calculating this from a molecular formula, there's no way for us to tell if these degrees of unsaturation come from multiple bonds, pi bonds, or if they come from rings. So we do not have that information from this calculation alone. We would need more structural information or other details. Okay, so let's try this out for the compound C5H8. So here is our stepwise step of how we're going to do this. The first thing we're going to do is calculate out the number of hydrogen atoms for a saturated compound with 5 carbons. So to do that, we apply our CnH2n plus 2 equation. And we figure out that what we're talking about here is that if we had a saturated compound, we would have 12 hydrogens. 2 times 5 plus 2, that makes 12. However, we don't have 12, so we know it's not saturated. In order to figure out the degrees of unsaturation, we're going to take our actual hydrogen atoms, subtract it from our expected hydrogen atoms, and then divide it by 2 because it takes 2 hydrogen atoms to make every degree of unsaturation. So here's what that looks like. 12 hydrogen atoms that we would have if it were saturated, 8 hydrogen atoms that we actually have in our molecule with our molecular formula. So 12 minus 8 is 4. 4 divided by 2 is 2. So we have 2 degrees of unsaturation in whatever our molecule of C5H8 is. We don't know, however, it could be 2 double bonds, could be 2 rings, or it could be 1 double bond and 1 ring. And we have no way of knowing from this information. Okay, so we have just gone through this and it seems pretty straightforward for compounds that are just carbon and hydrogen. And of course, as organic chemists, most of what we work with is carbon and hydrogen, but unfortunately, not everything. So we need to expand on this a little bit to be able to deal with other atoms that are not just carbon and hydrogen, right? So first, let's think about halogens. When you're doing this and you have a halogen, think about how if you had butane and you turned it into bromobutane, you have replaced a hydrogen with a halogen atom, right? You just exchanged one for another, but you have not introduced any degrees of unsaturation, right? Bromobutane does not have any pi bonds. It does not have any rings. So when you trade that hydrogen for a halogen, that's an even trade. You don't have to change your degrees of unsaturation. So when we go to count our actual hydrogen atoms, we're going to pretend that our halides are hydrogens. We'll see an example of that coming up. If we encounter an oxygen, we get to ignore it. Yippee! So we can ignore the oxygen because it does not change the carbon-hydrogen ratio. If you were to think about an ether, think all the way back to your functional groups about an ether, which is a carbon chain followed by a single bond to an oxygen, followed by a single bond to a rest of another carbon chain. Putting that oxygen in the middle does not change the carbon to hydrogen ratio, and it does not bring in any new hydrogens of its own. So we do not have to worry about oxygen at all when we're doing unsaturation. We just ignore it and leave it alone. Nitrogen is the hardest one to think about. I'm going to hopefully show you a picture that'll help it make sense, so you won't have to just memorize this, but we'll see. So nitrogen is trivalent, right? Typically trivalent with 3 bonds in a lone pair typically. So it's going to act like half of a carbon, and I'll show you what I mean by that in a minute. But mathematically, what we need to do when we are calculating our expected hydrogens in the saturated version, we have to additionally add in the number of nitrogens, because the nitrogen atom in a saturated molecule will bring 1 hydrogen atom with it, not 2, but 1. So instead of just a CnH2n plus 2, now we have to add in M for the number of nitrogens to our expected amount of hydrogens for this type of a molecule. So what do I mean by that? Well, first of all, let me break this down a little bit further and point out that this 2n plus 2 is just the same as our saturated hydrocarbon generic formula. This 2n plus 2 is the number of hydrogens based on the number of carbon atoms. But like I said, if we are going to insert a nitrogen in the middle of a carbon chain, that nitrogen would have the 2 bonds to the carbon chain, but it would also be bringing in 1 hydrogen in a saturated case. So we have to add in M, which is the number of nitrogens in the molecule, because each saturated nitrogen will bring in 1 hydrogen. So let's look at another way of looking at that. I showed you a picture like this when I introduced the generic formula for alkanes. But here I'm showing you why hydrogen brings in 1 carbon. So if we look at a carbon atom in the middle of the chain, that carbon is going to use 2 of its bonds to continue the chain in both directions, right? And the other 2 of its bonds are going to be to hydrogen atoms if we're talking about a saturated chain. When we insert a nitrogen into that chain, that nitrogen is going to use 2 out of its 3 bonds to keep the chain going, and a 3rd bond to bond to a hydrogen atom. And then that the rest of its octet will be filled by a lone pair if it's got no formal charges. So this kind of pictorial representation is the basis for this mathematical equation. When we calculate the number of hydrogen atoms expected in a saturated version of a molecule that has nitrogen atoms, we have to add the number of nitrogen atoms to our hydrogen count for this reason, right? All of the carbon atoms in the middle of the chain bring in 2 hydrogens. So that's this 2 times N for the number of carbons. There's 2 hydrogen atoms on the ends of a chain. That's the plus 2. And then every nitrogen brings in 1 hydrogen. That's the M. So let's see it in action. I think that'll help. So let's do an example. C4H9N. So the first thing that we do with our C4H9N is figure out how many hydrogen atoms would be if it were fully saturated. So if it's a 4-carbon saturated compound, it will follow this equation. So it'll have 2 times the number of carbons, so that's 8, plus 2. And then we have to add this plus 1 for the nitrogen. So our fully saturated version would have 11 hydrogens. It would have 11 hydrogens. So that's the fully saturated version. So now we can do the next step mathematically, or we can just do it intuitively by looking at the equations, at the molecular formulas here. Our fully saturated is a C4H11N, and our actual is a C4H9N. So that's 2 hydrogen atoms missing, which is equivalent to 1 degree of unsaturation. Okay, what happens if you're on a test or you're on a quiz and you've just forgotten this equation? You just can't remember how many hydrogen atoms the nitrogen brings in with it. Well, here's a cool backup plan for you. If you can't remember the calculation, you should know and remember that every molecule with a C4H9N molecular formula will have the same numbers of degrees of unsaturation as each other, right? Because we can do this in a calculation based only on molecular formula. So what you can do is draw any molecule with this molecular formula and then look to see, did you have to use a double bond or a ring to draw it? So here are some examples. You can draw any version of C4H9N that you want to, as long as you're still obeying the octet rule and trying to not have formal charges, right? And it doesn't matter what orientation, what branching, what anything you use. If you follow the octet rule and you keep everything with neutral in terms of formal charges, you will have a compound left that has 1 degree of unsaturation, because that's the math that it has to be, right? And so here in my examples, the one on the left has a 1 degree of unsaturation in the pi bond. The one in the middle has 1 degree of unsaturation in the ring. The one on the right has 1 degree of unsaturation in the pi bond. Note, the one on the right and the one on the left have their degrees of unsaturation as pi bonds. They have different molecular scaffolds, right? Different branching. But it does not matter. We're taking the same number of atoms, the same number of electrons, and just moving them around, rearranging them. It doesn't matter what the structure of C4H9N is, it will have 1 degree of unsaturation. Not 0, not 2, not 15, just 1. It doesn't matter what the structure is, that will be true. Okay, let's do another example. Let's try C4H7Br. So remember, halogens are going to count just like hydrogens in the actual hydrogen count. So let's go ahead and apply this. First thing we always do is figure out the number of hydrogens we expect for a saturated compound. In this case, we can apply our equation of CnH2n plus 2. We don't need to worry about the number of nitrogen atoms because we don't have any nitrogen atoms in our compound, right? So in this case, we have 2 times 4 carbon atoms, right? Plus 2 is equal to 10. So if we have 10 hydrogen atoms in our saturated version, the next thing we need to know is what the difference is. How many hydrogens do we have to take away to get to the structure? So in order to do this, we're going to take the actual number of hydrogens, subtract it from this number, and divide by 2. And the only trick here is to remember that in this case, the halogens count as hydrogens. So instead of 7 hydrogens, we're going to act like we have 8 hydrogens. So when we do 10 minus 8 and divide it by 2, that's 2 divided by 2, which is 1 degree of unsaturation. Okay. We can also do this for C6H7N. We can do this for anything, but this one we don't have enough time for, so I'm going to encourage you guys all to try this on your own. And we are going to move on to new topics. So before we move on to actual new topics, I want to kind of just remind everybody, it's a Monday, so I get that. I want to remind everybody about E1 and E2 elimination, which we learned about last week, and just kind of draw out a little bit of a compare and contrast to make sure to refresh everyone's memory on these. So as you guys know, E1 elimination is called E1 because it is unimolecular. So only one molecule, in this case an alkyl halide, is involved in the rate determining step. It is stepwise, so there's multiple steps in the sequence, and it goes through a carbocation intermediate. And we can contrast that with E2 elimination, which of course is bimolecular because it's called E2 elimination. It is concerted, so all of the bond making and breaking steps are happening in concert or at the same time. And that makes it stereospecific, meaning that the stereochemical information in the starting material can be translated to a particular specific outcome in the product. And we'll see more about that in the next couple of slides. Mechanistically, as a reminder, in E1 elimination, that first rate determining step is indeed unimolecular, so it's only the alkyl halide breaking that carbon halogen bond to create a carbocation in that first step. The second step in the case of E1 elimination, we have a weak base, which is a solvent in this case, deprotonating a carbon next door to the carbon the carbocation is at, so that it can create that other p orbital, an hybridized p orbital, and generate that double bond. So that's step 2, it's deprotonation of the neighboring carbon and pi bond formation. In E2, like I said, it is concerted, meaning we're going to have a strong base, and that strong base is going to deprotonate the molecule in a cascade sort of a mechanism where the deprotonation happens at the same time that sigma bond electrons turn into pi bond electrons, which happens at the same time as the electrons holding that halogen leave with the halogen. So we're going to get our deprotonation, our pi bond formation, and our leaving group leaving all in a single concerted step, where we go through a transition state that has partially formed and partially broken bonds. And again, because this is concerted, there is no intermediate, right? We're going through a high energy transition state directly to a product, no intermediates. And this is just a reminder that if we want to do a dehydration of alcohols, so we've been talking mostly about alkyl halides to make alkenes, but we can also do this from an alcohol, but it has to go through an E1 mechanism, and we have to protonate that alcohol first to get it to be a better leaving group in order for it to leave and create our carbocation intermediate. In that case, that step would happen before this step, so carbocation formation would actually be step 2 in an E1 mechanism, but carbocation formation will still be the rate determining step. Okay. Another couple of compare and contrast moments that I have for you guys. One is the energy diagram for an E1 elimination, right? So this should be a refresher from last week that this does occur in a 2-step fashion, so a stepwise fashion, where the first step involves a high energy step, an endothermic step that creates our carbocation. And then the second step is an exothermic step that creates our double bond. For E2, again, it is concerted and it is stereospecific. So the reason that I'm putting this picture here is to remind everybody that in order to do an E2 elimination, you have to be able to achieve an anti-coplanar transition state, which means that before you can even begin this reaction, you have to be able to pre-organize your substrate where the proton that is going to be taken off is directly across from or anti-coplanar to the leaving group. And that forced configuration sets the stereochemistry of your double bond, whether it's E or Z. So I've also put up some bullets here for E1 and E2 that I'm going to encourage you guys to take time on your own to go through and review. Nothing new here, but just a couple of reminders, and I'll point out a couple of key ones, but they're all important. So make sure you review this slide on your own later. In E1, that E or Z orientation is determined by the sterics involved, right? You're in a carbocation intermediate, which means all of these bonds to that carbocation are sigma bonds that can rotate. And so that will give you the most stable double bond, right, based on sterics. Also, because you have a carbocation, you can get rearrangements in an E1 elimination scenario. We can contrast this with E2 elimination, where the E or Z orientation is not at all relevant to sterics. The sterics have nothing to do with an E or Z orientation, because the E or Z orientation is set in stone by wherever the groups are relative to your proton and your leaving group when it is pre-organized as an anti-coplanar transition state. So the substituents on the left side of that plane will be on the same side of the double bond as each other, and the substituents on the right side of that plane will be on the same side of the bond as each other. Note that in both of these cases, the Zaitsev product, or the more substituted double bond, dominates. That's what I mean when that base, if that base has the option of deprotonating from a different neighboring carbon, it's going to choose the neighboring carbon that is more substituted so that you end up with a double bond that is more substituted. Okay, all of this should be a refresher, as is this slide. This is a slide that I showed you guys last week, just as a reminder that when you put a leaving group, a halogen leaving group in a ring system, then you have to keep in mind that in order to do an E2 reaction of that halogen, you have to be able to do a ring flip to get your halogen to be axial. Only when a substituent is axial can it have a proton in the anticoplanar position, right? So even though the equatorial form of the chair might be more stable, the axial still is formed sometimes, right? Some percentage of the time. And when that chair flip occurs, that is when an E2 elimination can occur, only when that halogen is axial. You don't have to memorize this though. If you understand the concepts here, if you understand how an E2 elimination works, then you will understand that it has to be anticoplanar. And if you understand the geometry of chair systems, then you will understand that you have to do that chair flip to get that reaction to work. Okay, so let's see it in action because it actually does make a difference. Here is a sample problem. And the question here is basically that this substrate, when it undergoes an E2 mechanism, gives only one single product, even though there are 3 different positions that could be deprotonated and 3 different products that could occur in an elimination reaction. So reminder, D stands for deuterium, which is just like a hydrogen atom. It just has an extra neutron in it. So a deuterium can be deprotonated the same way a hydrogen can be deprotonated just as easily. Well, not quite just as easily, but it can be deprotonated also. Okay, so think about this on your own for just a moment, and then we'll go through the answer together. But how is it, especially if you look at this, the proton up here at the top would actually give the Zaitsev product, right? So how is it that in this case, not only do we not observe the Zaitsev product, but we observe only one of the products that could come from deprotonation at the other carbon? Okay, so hopefully my last slide was a big old hint for you guys, but it turns out that because this is in a ring system, we have to orient our ring so that that bromine is in an axial position. When we do that, when we put our bromine in the axial position, we will see that the only options for what's anticoplanar are a deuterium or a methyl group, right? So if I look down this bond, I can have an anticoplanar arrangement, or if I look down this bond, I'll have an anticoplanar arrangement. But I can't deprotonate from this position because there's not a proton or a deuterium there, right? So the only position that I can deprotonate is the deuterium, which is indeed the reaction that occurs and the product that is observed, where the 2 substituents remaining on that double bond are both hydrogen atoms. This hydrogen atom that was facing up and this hydrogen atom that was facing up, those 2 hydrogen atoms could never be deprotonated to give you an E2 elimination because they will never be anticoplanar to that bromine. There's no Newman diagram you can draw that puts this hydrogen atom or this hydrogen atom anticoplanar to that bromine. So that is why you get only one product in this situation when it goes by the E2 mechanism. What if it were going to go through an E1 elimination? So I'm going to let you guys think about this and chew on it on your own and consider what possibilities exist for an E1 elimination. And I'm telling you right now, there are 3 different products, so you can figure that out on your own as a practice problem. We are going to move on to Zaitsev and Hoffman products. So this is going to be the last kind of technical piece of information that I have to share with you guys for this chapter. And the rest of the time, I only have a couple of slides on this. And then after this, the rest of the time I'm going to use to try to take a step back and go big picture on substitution and elimination and when each one happens. But first, I want to remind everybody that we just saw, actually, I'm going to go back and remind everybody. Here. On this kind of summary slide, notice that both for E1 and for E2, the Zaitsev product dominates. And I reminded you from last week that that means that when there's two different options for where a base can deprotonate, it'll deprotonate from the more substituted side so that you get the more substituted alkene, which is more stable. But I'm going to jump back forward again. And I showed you guys this last week, right? We talked about this kind of in depth last week. In the example that we have on the slide here, you could deprotonate the blue pathway or the green pathway to get different products. And the blue pathway is more favored at 90% because it yields a tri-substituted double bond, whereas the green pathway yields a di-substituted double bond, which is less stable. Even though there are 3 times as many of the type of proton that could be deprotonated to go the green pathway, it's only representing 10% of the pathways. But think about it for a second. We're organic chemists. And so sometimes we want to synthesize a particular molecule, right? We have a target molecule in mind. We have a cancer drug that we need to synthesize, and it has a double bond in it that is di-substituted instead of tri-substituted. How do we affect a synthesis that could give us the less substituted product? And I want to pause here for a moment and let you guys know that this sort of way of thinking about things is something that I'm going to try to be introducing to you guys subtly over the next couple of weeks, because it's going to be a big part of Orgo 2. The more reactions you guys learn, the more you're going to be expected to be able to put them together in the right sequence to synthesize something in particular. And so being able to not just know how to make a double bond, but how to make a particular double bond in a particular molecule with the constraints of that molecule is going to just become, even more and even more important. Okay. So in order to do that, we have to, as chemists, come up with a different method, right? So if we want to synthesize the less substituted product, but we know that E1 and E2 both favor the more substituted product according to Zaitsev's rule, what do? Well, what we can do as chemists is we can use our rational thought processes and our chemical intuition, and we can realize that in order to do an elimination on the less substituted carbon, we can take advantage of the fact that a less substituted carbon is actually usually less sterically hindered. And so if we make a base that is really bulky and big, then it will be harder to get to the more substituted protons and easier to get to the less substituted. So we can use the steric consideration to our advantage. So the bases that I'm showing you on the screen here are considered bulky bases. You can see that they have kind of a lot of stuff coming off of the atom or a nearby atom where the negative charge is or where the electron density is built up. And so these types of bases actually do not follow Zaitsev rule, and they give what's called the Hoffman product after the guy who figured this out and published on it first. So I'm showing you all of these to show you some examples. I am only ever going to use tert butoxide when I ask you guys questions on tests and quizzes. So this is the one that you really need to know. But, in Orgo 2 with other professors, you might see some of these other ones. But I think structurally, you can look at these and see that they're bulky. So what do I mean by bulky bases favor the Hoffman product? I've got 2 examples here where we're looking at the same exact substrate, right? We have a secondary alkyl halide, and under an elimination reaction, we can deprotonate the green protons or the blue protons. And the blue protons, actually, this methyl group has essentially blue protons also because they're the same type. The green protons are a little bit more hindered because of the methyl group out here, whereas the blue protons are kind of on the edge of the molecule. They're a little bit easier to get to. So if we have ethoxide, so the deprotonated version of ethanol, if we have ethoxide, That is just a normal base. And so it is going to form the Zaitsev product preferentially. And a little bit of the less substituted product will form also. But most of the products, the major product, will be the Zaitsev or the more substituted double bond by the deprotonation of a green proton. If, however, we trade out our ethanol for tert butoxide or T-butoxide, and of course, we're going to put this in tert butanol instead of in ethanol, because once we deprotonate, we'll have the alcohol solvent. So if we switched this Belcki base of tert butoxide, that tert butoxide, because it is bigger, has a little bit harder of a time getting to the green protons because they're a little bit more hindered. And so it's going to go grab one of the blue protons, which are less hindered. And now we have switched our kind of ratio, and now we're favoring the less substituted double bond or the Hoffman product. So that's a Belcki base, and it favors the Hoffman product. Same substrate, right? Same substrate. It's just a different base that we've chosen. Notice that both of these are stronger bases too. Okay. So that is the last kind of technical piece. And the rest of what I want to do is kind of take a step back and put this together and look at how do we decide which mechanism to use when we're faced with an alkyl halide and a nucleophile or a base. So think about this for just a second. If you have an alkyl halide showing up in a reaction with something like methanol or methoxide, those are nucleophiles and bases often go hand in hand. So now we've got these 4 different pathways that can all occur on alkyl halides in the presence of a nucleophile or base, right? In lots of cases, more than one pathway will happen and you'll get a mixture. But how do you know which one is the most likely and how do you know which one is favored? So let's think about this for a second. You guys already have all of the information you need to answer these questions. You already have it from chapter 6 and from what we've learned so far in chapter 7. I'm going to try to put it together for you in a new way so that you can be a little bit more rational in your approach to these types of questions. The 2 most important things to look at, are the strength of the nucleophile or base and the sterics or substitution level of the substrate. And that'll help us determine like 80% or 90% of what we need to determine. If you have a strong nucleophile or base, those strong nucleophiles or bases help us to favor a bimolecular pathway, either SN2 or E2, bimolecular reactions, because they're strong nucleophiles or bases, right? They're reactive, so they're going to go out and make something happen. That's the kind of the take home for the nucleophile base strength. And the take home for the sterics are that primary halides almost always are going to be an SN2 mechanism. They're almost always going to be an SN2 mechanism. Whereas tertiary halides, we know they cannot undergo SN2. We learned that back in chapter 6, that that's not allowed for tertiary halides. So they will be either SN1, E1, or E2. And typically you'll get a mixture. So notice secondary halides aren't on this list. I have a whole slide for secondary halides because they're the hardest ones to determine. When you have a higher temperature, that can sometimes indicate to you that you have an elimination process. But keep in mind, you also still need a high temperature to do SN1 reactions to help that alkyl halide bond break. And also bulky bases favor eliminations because anytime you put bulk on a base, it is not a good nucleophile anymore, right? So even if you have a relatively unhindered electrophilic carbon, if you have a bulky base, it's still hard for that base to act as a nucleophile because it has to be able to fit into a spot to reach that electrophilic carbon. Okay, I told you I had a whole slide on secondary alkyl halides, so here we go with the secondary alkyl halide slide. These are always going to be more challenging. The same way, like if you have, it's not black and white, it's the gray area of the spectrum, right? So if you have a strong nucleophile or base, you'll promote bimolecular. If you have a weak nucleophile or base, you'll promote unimolecular. That's the same, consistent with what I just said on the last slide, that also applies to the other substrate types. I'm going to take a moment to remind everybody that There are some cases, most of the time a strong nucleophile is a strong base, but there are 1 or 2 examples that we know of that that's not the case. And those are really limited to bromide and iodide. These are strong nucleophiles, but the conjugate acids of bromide and iodide are strong acids, so they're weak bases, right? So these examples are strong nucleophiles and have limited basicity. So those are going to favor SN2 reactions always. Okay, so here is a little pictorial representation. We have a secondary alkyl halide and methoxide, which is a strong base and a strong nucleophile. So we know that it's going to be favoring bimolecular pathways. And indeed, both conditions are going to be the case. It will do SN2 chemistry, where it directly displaces this carbon bromide bond, and it will do E2 chemistry, where it will eliminate in a predominantly Zaitsev fashion. If, however, we have methanol, so just the protonated version of methoxide, methanol, because it's a neutral molecule, is no longer a strong base or a strong nucleophile. It is a weak base and a weak nucleophile. So it is going to favor unimolecular pathways, E1 or SN1, right? And in fact, both occur in a secondary alkyl halide, just like both E2 and SN2 occur in a secondary alkyl halide with a strong base or strong nucleophile. Okay, so just to put this in a couple of different terms, if we look at substitution levels on an alkyl halide that is a primary alkyl halide with a strong base, all of these examples are going to be with a strong base, that's going to go almost entirely SN2, right? If we look at a tertiary alkyl halide, SN2 is not allowed. SN2 is not allowed, but we know that we have a strong base, so that's going to favor bimolecular reactions. So that tertiary alkyl halide is most likely to undergo an E2 elimination. If we have a secondary alkyl halide, we have a strong base, bimolecular reactions are occurring, so we will get both E2 and SN2 products. Okay, so let's look at this in a couple of sample problems. Here's the first one. I have this written as predict the mechanisms and products of the following reaction. I'm not asking you to write out the mechanism, but what I'm saying here is that you need to predict the products, but in order to be able to predict the products, in order to know what the products might be and the stereochemical consequences, you have to be able to know which mechanisms are at play here. So let's look at this problem together. We have a tertiary alkyl halide, right? And we have methanol and heat. Is methanol a strong or a weak nucleophile slash base? It's neutral, it's protonated, so it is indeed weak. So we have a weak base and weak nucleophile, so we know we're going to favor unimolecular. We have a tertiary alkyl halide, which means we're going to have a mixture of products that depends on the nucleophile base strength, which we just said was weak. So the first thing that's going to happen is that we're going to not deprotonate, we're going to break our alkyl halide bond, create our carbocation, right? And then from this carbocation, we will get both E1 and SN1 reactions occurring. In an SN1 reaction, the substitution, our methanol nucleophile will create a new oxygen-carbon bond right here. And then after deprotonation, this would be the product. Elimination is also occurring then because our methanol can act as a nucleophile or as a base. And when it's acting as a base, it can deprotonate on either of the neighboring carbons in the ring. And it turns out both of those positions will lead you to the double bond being in the ring. Or it can deprotonate out of the methyl group, which will lead you to the double bond being outside of the ring. And the major product that happens is the one in the ring because that is the Zaitsev product. Okay, I'm out of time, so we'll cover the rest of this next time. I did have another sample problem for you guys, so I will post that with the slides today, and I really strongly encourage you guys to try this on your own. I can stick around for some questions. It looks like somebody asked in the chat box and I missed it. How do you tell which were axial with the wedge and the dash bonds? Okay, so that goes back to our chapter 4, I think it is, chapter 3 about drawing chair forms. So let me flip back to that screen. Okay. This is actually the screen we want, right? So
yes,
we have all of these wedges and dashes. I have drawn just one chair form here, but remember this chair form is a rotational conformer. So this chair form can flip and it is in equilibrium with the chair form where the bromine and the methyl group are axial. The chair form where the bromine and the methyl group are axial is actually the more stable chair form. But in that position, you cannot do an E2 elimination on the bromine. So all I've done here is to draw this flat representation of cyclohexane into a chair form representation of cyclohexane where I've been sure to make my bromine in an axial position. When I draw my bromine in the axial position, it's above the ring. So the corresponding hydrogen on the same carbon atom is below the ring. Likewise, on the next carbon atom over, our hydrogen is coming up. So that's going to be going up from the ring. Our deuterium is going down. So that's going to be going down from the ring. So the conversion from this flat representation to drawing it as the chair form with the axial with the carbon bromine bond in the axial position is just an application of drawing the chair form from flat representation to chair form that we covered in chapter 3, I think. Oh, no,
thank you.
It was in chapter 5, actually, because of stereochemistry. Okay. Did that answer your question, Alexis?
Yes, thank you.
Cool. All right. Somebody asked about the test again regarding the test. It is graded, but I want to take some time to look through it and just kind of make sure everything is all set. So I should be releasing those grades later today or tomorrow. And then somebody wrote how to go over if it's a primary, tertiary, or secondary halide. So in the case of what we're talking about here is that whatever halide it is, it's named that for the substitution level of the carbon that's attached to. So in this example here, if we look at this carbon atom that has the halogen attached, that carbon atom has carbons at 2 positions. It's attached to 2 carbons. That makes it a secondary carbon, which makes this a secondary halide. And you can go back and review that in the slides from the first lecture on chapter 7, which should have been on Wednesday of last week. Okay, any other questions? If not, then I am going to go ahead and release you guys from